Good morning, class. I'll briefly outline the Kruskal's algorithm and talk a little bit about union find. I thought it was too much, but then I thought, let me complete Kruskal's algorithm. And as we said, the idea is that you start with, basically you have disjoin each initially each vertex is in its own set. And basically the minimum spanning tree property is what is used. So basically all low cost edges have to be in the tree, as we saw. And basically what we will do is, so you start with this. I'll talk to you a little bit about this and then talk about the complexity. So you have a graph which is given, and G is a graph. And it returns for you Q, which is a set of Q, which is a set of edges. And so initially, you look at the number of sets that are there, and this number of sets is equal to the number of vertices. And once all the, if it's a connected graph, and the number of components becomes 1, you're done. Okay. So we have a variable called num_comp, which tells you how many sets are there. Let's say this is type integer. And the edges, you can put in a main group. And the components are essentially the sets. Okay. U and V are, let's say, of type vertex. E is of type edge. And next comp is the C. This is just a complete variable of type integer. Okay. And ucomp and vcomp are, let's say, one that belongs to one set, another component. Basically, these are component names or set names. Okay. So initially, you create a tree, empty tree, and then let's say we also make type edge, and sorry, this is a menu, and e dot make null. We create an empty seed. Right. And next comp is a variable which is initialized to 0. And number of components, num component, what we call it, num comp is initialized to cardinality of the number of vertices, equal to the number of vertices. So what we do is, for V in V, do next comp plus plus, and you initialize the set. Okay, assuming there is a set. Next comp and B comma So basically, it gives you the number of components and increment the number of components. Put it in the component list. It's a set of sets. Okay. For E in E, we insert the edges into a. What do? I call it E and O. This is sorry. This is an edge vector. Do edges dot insert of E. So we insert all the edges into a menu. And while the number of components is greater than 1, we do the following. E is assigned the value of edges dot deletment. So we take the most minimum edge. Suppose it is E, which connects two vertices, E and E. So what we do is we find the name of the component in which the vertex is, because it's there in components now. I said component is a set of sets. We compute recom, find of components. If ucomp is not equal to ucomp, then you merge. So ucomp is a set. So we merge of ucomp. This is a very crucial operation which you will learn about in your next course. This merging will decide how complex the find operation can be. Okay. Then number of components gets reduced and inserted into the tree. Insert that edge into the tree and this end while, and this is the Kruskal's algorithm. Okay. Start with this. So repeating again, the creator. So this is one that keeps track of the number of sets that we have. Edges is put in a min heap, sorry, not stand corrected. And components are essentially sets. E and B are vertices. E is an edge. Next comp is a temporary variable. Ucomp and vcomp are component names. So we initialize the tree, we initialize the heap. Next comp is initialized to 0. Number of components is the total number of vertices in the graph. So for B equal in B, what we do is initialize this. So this is N4 in here. And this should be an N4. So basically we insert you create a set for every vertex. And here you insert the edges in the meeting. And while the number of components is greater than 1, you delete the edge. And suppose the edge is U and B, you find between you vertices U and B, you get the component name of vertex U, component name of vertex B. And then what you do is you ensure that component U and V are, because when you're doing ensure that you want to connect across sets, then you merge the two sets. And okay, so let us see how this whole thing gets set up. Okay. So what we do is the following. So let's look at that. So initially, in this example, when we start out, 1 is in its own tree, 2 is in its own tree, and so on, up to 6, its own tree. Okay. Then what we're doing is, or in its own set, then we are connecting 1 and, this example, 1 and 3. So 1 is here, and this is 3. Okay. So this is in its own set. Then we have the 4 and 6, which are in their own sets. Then we have 2 and 5. Now, what we do is we have to merge these trees. So the next smallest edge is from 3 to 6. Okay, so what we do is, now I can take 3 here and then connect this tree 4 and 6 like this. Okay, basically that 4 points to this 3 and 3 points to 1. And then we find that 2 and 5, it'll connect to 5. And when we merge these sets, it's possible that I have 3 here, 1, 3, 4, and 6, and 2 and 5. So this is the tree that we might finally end up with. But clearly, you can have examples where I have, this is one example that is there. So it's possible that when we are merging, 1 gets merged with 2, 1 and 2 gets merged with 3, 4, 5, and 6. So it can become a very long tree. So there are techniques. So this is primarily, so basically what happens is, if I want to find the set to which 6 belongs, it belongs to the set 1, and you have to go through a huge chain, because 5 is the parent of 6, and 4 is the parent of 5, and so on. So search can become, find operation can be quite expensive. So this can be fixed by doing the merge differently. And what is done is something called rank is taken into account. And and what you might do is you start out with 1 and 2, and 3 would have been merged here, and so on. Okay, but this is beyond the scope of this. So this is what we did essentially is what is called a union and find operation. Okay, and we saw how we can use it to build the Kruskal's algorithm for minimum spanning tree. Okay, so the next topic that I want to talk about is traversal of trees, traversal of graphs, and particularly have 2 types of traversals called the depth first traversal and the breadth first traversal. Okay, we'll look at both directed and undirected graphs for this. And so what are these traversals? What do these traversals enable? That there are many problems that require that the edges and vertices are visited in a systematic manner. And that is where these two traversals come into the picture. And depth first search, as it's called, is a generalization of what we already did. Pre-order traversal of trees. Okay. And let me just give you the basic idea. We'll talk in the context of directed graphs, because there are some new definitions come into the picture. And so you have a directed graph in which all the vertices are initially marked as unvisited. Then DFS works as follows. Select a vertex V of G as a start vertex. And then we mark it as visited. We then visit each vertex adjacent to V recursively using DFS. Once all vertices that can be reached from B are completed, the search from B is complete. Then we next select another unvisited vertex as a new start vertex. And we repeat this until all the vertices in the graph are visited. So let us just sketch this algorithm. So what we do is, let me call this DFS of operates on a graph G, and T is a, actually this could be a forest of trees. We'll see why. For each V in G, mark of V, assign the value of unvisited. End for each. Then we start for V, assuming that the vertices are numbered from 1 to n, do if mark of V is unvisited, then we perform a function called DFS of V. And we're just using lowercase for this, okay? And DFS. Okay. This module DFS will look something like this. Vertex. Say W is a vertex. We first mark V as visited. Then for each vertex, W that is adjacent to V, we say it is in L of V, where L of V corresponds to the vertices that are adjacent to V. Do if mark of W equals unvisited, then we start with DFS of W. Okay, so this is how it goes through as deeply as possible. And DFS. So what are we doing? We're starting with the vertex V here. And we look at all the vertices W which are adjacent to V. Suppose L of V contains the vertices that are adjacent. Then if mark of W is unvisited, then you repeat DFS. So this is what we mean by going as deeply as possible. So let's take an example. And of course, DFS can start at any vertex. So I have a directed graph like this. It can be run on an undirected graph also. But I'm taking a directed graph because it gives us some new definitions of vertices, of edges. Like this. And graphics. Now, oh, sorry, let me change it here. Edge versus. Suppose we start at the vertex A. Then clearly from A, I can only reach B. Now B is adjacent to C and D. And from D, there are no edges that are going back to E, so I cannot, it's already visited. And from C also, it's going back to E. So what happens? I start at E now and I get F and G. Now from C, I have a arc that goes to A. I have an arc from D that goes to A. Sorry. So, and we have an arc that goes from D to C. Similarly, we have an arc from G to D. And we have an arc from F to B. Okay. These are called tree arcs. These are called back arcs. And these are called cross arcs. Okay. Actually, there are 4 types of arcs in this. So notice that we got a forest in this example. There are 2 free trees that we have over here. Actually, we have 4 types of arcs. Basically, we can have forward arcs, backward arcs, cross arcs, and tree arcs. To distinguish between these arcs, we assign a DFS number to each vertex that is greater than or equal to its descendant. Each vertex V of V. That is a descendant of V, of a vertex V, is one such that, or if a vertex is a descendant of V, only when DFN of V is less than or equal to DFN of W. Each vertex V that is greater than or equal to its I'm saying something wrong here. The vertex B will have a smaller number and its descendant will have smaller than. And what we do is W now, here W is a descendant of V. Okay. And DFN of V is less than or equal to DFN of W, which is less than or equal to DFN of V plus number of descendants of V. Why is important? It will tell us whether it's coming from another tree. Forward arcs are defined as, in this example, there are no forward arcs, go from a lower numbered vertex to a higher numbered vertex. And it's not a tree arc. That is, we could have another arc which goes from maybe A to C, but you know, it's not part of the tree. Okay. And cross arcs are generally at the same level, higher numbered vertices to lower numbered vertices. That's all. So in this example, we saw C2A is a back arc. Okay. And arcs like D to C or G to D, which are not tree arcs, neither are the ancestors or descendants, are called cross arcs. And notice that when you're looking at cross arcs, it's so important that DFS behaves like pre-order, going from left to right, because you're numbering. Okay. Very important. And left to right, this implies what? Cross arcs are always from right to left. Okay. DFS has applications. We look at one particular application. For example, all of you are looking at courses, and courses have prerequisites, or in the context of programs, for example, you may have multiple programs and there might be prerequisites that certain, like an assembly chain, some tasks must be completed before others. Basically, there is an ordering. This is called a topological sort. Okay. So what is topological sort formally? Sort is a process of assigning a linear ordering to the vertices of a particular type of graph called the directed acyclic graph. Let me give you an example for what a diag is. Let's say I'm doing expression evaluation. Remember we drew a tree for this. I can write something like this. Points to its parent. And see, then this one, for example. So, so what's the advantage of that? This is what is called a directed acyclic graph. All of them are doing parent pointers over here. So if I want to evaluate this expression, what is nice about this? There's a common sub-expression which does not get evaluated again. Remember when we do the infix tree for this expression, it would have gotten evaluated again. So DAG is a way of ensuring that sub-expressions do not get evaluated again and again. And this is acyclic because there are no cycles over here. Okay, so let's take what this topological sort is all about. Vertices C1, C3, C5, and have C2, C3, C4, and C5. Then actually C1, C2, C3, C4, C5 is a topological sort. It's not used in DFS, but we'll see how to use DFS to get this. The topological order. And the algorithm is slight modification to top sort. B is a vertex here. What we do is take a vertex W. Let's see how we can use depth first search to do it. You can also do it using depth first search. That's what has been done here. Mark BS visited first. For each vertex, so we're doing exactly the same thing as in the capital DFS algorithm, which we're calling top sort. Small DFS, we're going to call it top sort. W in L of V do if mark of W is unvisited, then top sort of W. The difference is the following. You output W when it finishes the, remember in pre-order, what do we do? As soon as you visit it, you mark it and output it. What we mean is here, when top sort finishes all vertices that are adjacent to a given vertex you print that vertex. That's what we do here. And what it gives you is, it gives you in the reverse order. The reverse order of the topological sort required. So you can store it in a stack, and pop to get the correct. Let's see this example. On these examples, let's see what we get. What did we have? We had C1, C2, C3, C4, and C5. So what we do is, let's say I start with C1, C3, C5. So I've exhausted. So I output all the elements. Oops. Output all the elements. So what will I output? C5, C3, C1. Then I start with C2. Then I get C2 and C4. Then what will I output? C5, C2 in the reverse order I put in there. So this is the order in which we are processing C5 and C2. Yeah, C4 and C2. Sorry. So if you look at this topological ordering that we've got, C5 should be completed. So I want the reverse order. So we have here, what do we want? So you reverse all of this. So I have C5. I start with C1 and we're putting it in the other order. C5, C3, C1, C4, C2. So C2, C4, C1, C3, C5 is the correct order for the topological sort. Okay. So how nice would it be if, for example, if you want to take this course, it will tell you what is the order in which you have to take them. Okay. So this is what topological sort is all about.